All right, after our trek through Chapter 3 and related rates earlier this week, we are going to go into a much nicer, gentler world. We're going to talk about critical points, maximums and minimums, and a little bit of graph sketching. So let's first define what these terms are. Make sure you've got your notes all ready to go, and we'll get started. So a critical point, if you remember, is just where the slope of a curve equals 0. And there's 3 different places where that happens. It might be a maximum, it might be a local maximum, a local minimum, or it could just be a critical point where things kind of flatten out and then will continue in the same direction they were going before. Now, to find the critical points, all you want to do to start is take the derivative so that you can find dy dx. In this time, we got a big old quotient rule. So then the derivative of the numerator is just going to be 1, thank goodness, that makes it easier, and the derivative of the denominator is going to be 2x plus 1, so that when we differentiate it to find, in this case, f prime or dy dx, you can use either notation, you end up with x squared plus x plus 1 times 1 minus 2x plus 1 times x plus 1 in the numerator, all over x squared plus x plus 1 all squared in the denominator. Now you can do some algebra to simplify this, but I'm going to hold out with that in this case for a second because the next thing I'm going to do is just set equal to 0, and that's going to let me cancel out a lot of things really fast. Because the first thing I'm going to do is set equals 0 is I'm going to multiply by this denominator. And when I multiply by a denominator to 0, oh, what's so nice? Times 0, still 0. So now I dealt with that very quickly, and it's going to make my rest of my simplifying a lot easier. So the next thing I'm going to do is FOIL these last terms, and then I'm going to simplify there. We've got x squared minus 2x squared, which will be negative x squared. X minus 3x, which is minus 2x, and 1 minus 1, which cancels out. And this is a nice quadratic we can solve with factoring, and so then we get x equals 0 and x equals negative 2. And those are our critical points, x values. If it asks for points, that also means we want to find their y values, so we can just plug into the original formula. And we end up with 0, 1, and negative 2, negative 1/3. And so do pay attention in the problems if it's asking for points or the x values at which there are critical points, because the format of the answers will be slightly different. So once you've found the critical points, the next question is often going to be, well, are those going to be a maximum, a minimum, or is it going to be neither? These are also called extreme values. So maximums or minimums would be extreme values or extrema. And there's a couple ways to do this. The way I think is easiest, and the way a lot of you will have done this before, is to just draw out a number line, which would have your x values. So in this case, 0, whoop, that doesn't come first, negative 2, and then 0, and then you pick some points that are in between those, like this, where you have, let's say in this case, negative 3, negative 1, positive 1. And then you look at what kind of values there are for f prime. So we know here it's 0 for these ones. If I plug in negative 3 to f prime, which we remember here as negative x squared minus 2x over x squared plus x plus 1 squared, if we plug in a negative there, we would get negative 9 minus negative 6, so plus 6. So we have a negative in the numerator, and then we're always going to have a positive in the denominator because it's squared. So that means that it is going to have a negative value. Then with negative 1, we'd have negative 1 plus 2 in the numerator, so that's going to be positive. And then at positive 1, we would have a negative in the numerator and a positive in the denominator. So that means that it's all going to be negative. If you want to find out what these exact values are, feel free to plug them in if you don't want to take my word that they're going to be positive and negative. So what this tells us is that on this part of the function, so negative infinity to negative 2, we have a negative slope. Here we have a positive in this interval, and then we have a negative. Now, obviously I'm approximating those with lines, but you can imagine if I filled in the curves, this tells us about the behavior. So what this tells us is that we have a minimum at negative 2, and we have a maximum at 0. You'll eventually just be able to be like, oh, well, it goes negative to positive, that's a minimum, positive to negative, that's a maximum. If two consecutive ones were the same, then it would be neither. Now, these are both local extrema, meaning that this is the minimum for everything around it, this is the maximum for everything around it. But you can imagine here, this might go up farther, so there might be another number even higher than this maximum here, and there might be one lower than this minimum here. And those are called absolute maximums and minimums. And we care about these most on a closed interval. So on a closed interval, you're still going to find those critical points that we just did, but you're also going to want to test the endpoints, because what might happen is that you might have something like we suggested there, where this is what f of x looked like, where we have a minimum here, but the actual minimum, if this is a closed interval, is all the way down here. And same thing with the maximum, right? This might be the maximum here or this one, and it's hard to tell without actually plugging in and testing. So in this case, we're given the interval negative 1/2 to 4, and we are given f of x is equal to x cubed minus 3x squared plus 1. So the first thing we're going to do is, as it says here, find and test the critical points where f prime is equal to 0. So let's find f prime. And here we're just looking at a polynomial, nice and straightforward, 3x squared minus 6x plus 0. Set that equal to 0, and you get 3x squared minus 6x. And when we factor that to 3x times x minus 2, this tells us that our critical points are at 0 and positive 2. Now, the way that I test all these values, I don't really care right now to test if those are maximums or minimums, because what I'm going to do is create a t-chart of my x values that I'm interested in, which will be one end of my interval, my two critical points, and the other end of my interval. And then I'm going to just ask myself what the y values are. The smallest y value I find is the absolute minimum. The biggest y value I find is the absolute maximum. And so I'm just going to plug in all these into my original function here. So when I plug in, so f of 1/2 would be 1/8. Absolutely get out your calculator if you want to check my work. F of 0 is 1. F of 2 is negative 3. And f of 4 is 17. So looking here, negative 3 is my smallest one. So this is my absolute minimum, and 4 gives us our maximum of 17, which means that I would say that the absolute max is 17 at x equals 4, and the absolute minimum is negative 3 at x equals 2. Now, we are also going to use these pieces of information to identify graphs based on their derivatives. So this is a very common type problem that you saw last year, which is identify which graph is f, f prime, and f double prime. Now, there's lots of ways to go about doing it. The first thing that I'm going to do is I'm going to compare where things have critical points and where things equal 0. And the reason for this is that f will have a critical point, and then f prime will equal 0. Same thing is that if f prime has a critical point, then f double prime will equal 0 at that same number. And so that's just a nice way to start gauging which one is which. So if I start by looking at blue, blue has only one critical point, and it is here, because that is where the graph is flat, and the point that is 0 underneath there is here. So what this tells us is that if the blue line is F, then the red line would be F prime, or it's F prime, which means that the red line is F double prime, because that's where our critical points line up. Now, another set of critical points that line up are, if I'm looking here on the red graph, those line up here on the green. And by line up, I mean literally line up, like they are in a line. So this tells us that the green curve is the derivative of the F curve, of the red curve, I should say. So if this could be F or F prime, which means that green could be our F prime or F double prime. Now, as we've worked this out, we now have all of our possible situations, and the ones that make the most sense is to say that, well, since F is either F prime, since red is either F prime or F double prime, or it's F prime. That means that these are the only ones that it can be, because it's in both our options. So therefore, red is our F prime. And as we said here, if red is F prime, that means that blue is the regular function. And then here, that if red is our F prime, that means that green is the derivative. And now we have assigned which one is F, F prime, and F double prime. All right, last example that we're working on is asking about intervals of increase and decrease. So we're going to start off just the same way that we did before. And whenever you're asked for intervals of increase and decrease, again, you're going to start off by asking yourself, where is the function equal to 0? So we've got F prime here, 12x cubed minus 12x squared plus 24x. I'll let you do the algebra yourself, but we end up with 0 for our critical points is equal to 12x times x minus 2 times x plus 1, which gives us our critical points at x equals 0, 2, and -1. And then we're going to do our number line chart just like we would to find the intervals of increase and decrease. We have our x values, so -1, 0, -2, and we are going to pick our other points. Here I'll pick -2, -1/2, +1. Whoop, I picked up a weird negative on there. And then 3. Let me erase that. And we're going to compare that to our F prime values, which we know here are 0. And when we plug in -2, we end up with a negative number. For -1/2, it's positive. For +1, it's negative. And then for +3, we end up back with a positive number again. So therefore, our intervals of increase, I'm just going to do a little erasing, are where the F prime is positive. So increase is going to be from -1 to 0. I'll write it in interval notation, so -1 to 0 with open bounds, plus, so union, here we have 2, and then all the way up. So we would say from 2 to infinity. Our intervals then of decrease are the complement of that. So -infinity to -1, union, and again, this is 0 to 2. And those are our intervals of increase and decrease. Now, another question we might be asked is our maximum and minimum values. You can use this table here to say, okay, well, we've got a maximum at 0, because we're going up and then down, and we have two minimums at -1 and +2. So here, and we have, these are our x values for our maximum and then our two minimums, and we'll need to use the original function to find the y values. When I plug in 0, f of 0 is 5. When I plug in -1, we end up with a y value of 0, and f of 2 is -27. So those are our maximum and minimum values for this function. Lastly, our points of inflection. These are the critical points that we have of this second derivative. So it's where the second derivative equals 0. So if you remember, f prime was this polynomial here. So in this case, f double prime would be 36x squared minus 24x minus 24. Nice quadratic. We can try factoring this one, but we do end up with something we have to use the quadratic formula for. And we will end up with our x values that are equal to, I'm just going to bring it over here so I don't have to erase, x is approximately equal to 1.215 and -0.54. And if we remember points of inflection, what happens at those is that the curve of the graph goes from either being what's called the concavity changes, so this would be a point of inflection here and another one here. These two parts of the graph, we call those concave down, looks like a frown, and then this red part at the points of inflection, it changes, and we call that concave up. When the graph is concave down, it means that the second derivative is negative, so it's less than 0, and when it's concave up, it means that the second derivative is positive or greater than 0. I know there's a lot of things that we just went through in this lesson. You'll notice that the homework is broken up into 2 sections, so please do at least some from each. Have a great day, and I'll talk to you later. Bye.